I think they're all due Wednesday.
Okay, is there any questions on the homework? Are there any questions? So no questions on the homework? Everyone's good? Due tomorrow, I believe.
Yes, I do have a whole. The very last question, please. 10.9.10. It's okay. I'll read it to you. So, okay, yeah. Okay, it says that a 70 kilogram runner loses 0.5 kilogram of water each hour through evaporation of perspiration in order to maintain a stable temperature. And then it says the latent heat of water is 2,440 kilograms per kilojoules per kilogram. And the
Okay,
you want
you go through that again. I got distracted by people's phones for some reason.
okay.
But is that the
The runner.
is that where the okay?
Yeah, he's 70 kilograms,
Okay.
and he loses 0.5 kilogram of water each hour through sweating. And then it says the latent heat of water at the skin is 2,440 kilojoules per kilogram.
40
Yeah.
kilojoules per kilogram.
And then the average specific heat capacity of the body is 3.5 kilojoules per kilogram per Kelvin.
3.5
kilojoules per
kilogram. Okay.
per Kelvin.
Yeah.
And then it says if he stopped perspiring, how much would his temperature rise in the following 30 minutes?
Oh, okay. So temperature increase. All right. So, and this is my understanding would be that this would be when the sweat gets to your skin. Is it?
Yeah, it says
We
at
also
the
have to
skin.
heat it up to the. We also have to heat it up from skin temperature to boiling. No, we don't.
Oh.
We just have to do the evaporation, right?
Yeah, it doesn't say to boil, it just.
Yeah. So I think this is just the. This is how much heat's carried away when it transforms from a liquid at room temperature or at body temperature to gas. I think that's what it means by latent heat. Can you read what it said, latent heat on the skin?
Yeah, it says the latent heat of water at his skin temperature is that value.
So that's the amount, so when water evaporates at a given temperature, that would be then how much heat's carried away. So you're not raising up to boiling, you're just letting it evaporate at that temperature, and so this will be a little bit higher than the latent heat of vaporization.
So would it be like in half an hour, do you cut the 0.5 kilograms per?
Yeah, well, let's see how much energy must be taken away in half an hour.
Okay.
So the Q of the water, this is the heat that's taken away by the water, which is Q, would be mass times L. So where this would be the mass of the water that's taken, that's evaporated, and the heat of the water. And so that would be 0.5 kilograms per hour times 2440 kilojoules per kilogram. So that would be 11220 kilojoules per hour. So that's the heat that's taken away, and he maintains his body temperature at that heat, right?
Mm-hmm.
So this is how much heat he's generating every hour
Every hour.
by running.
So then half of that?
So in half an hour, the person generates or would heat up or generates a certain amount of heat to heat up, and that'd be 610 kilojoules of generated. And this is the amount of the heat that would be used to heat up the body. So let's go back over to here and see how much the temperature increase would be.
So you need 610 equals C times 20.
So 610 kilojoules is equal to the heat capacity times delta T. This is equal to the mass of the person times the specific heat, okay, big C, for heat capacity, times the change in temperature.
So it would be 70 kilograms.
Yep, so this would be 70 kilograms
3.5.
times 3.5 kilojoules per Kelvin per kilogram times delta T. All right, now we need to solve for delta T. So what's the 70 times 3.5?
245.
Okay, so take that 610, divide by 245, what do you get?
2.5.
What's that?
2.5.
So that'd be roughly, I don't know, a little over 4.5 degrees Fahrenheit that a person's body temperature would heat up at that time. So, you know, you go from 102, 103 degree temperature. That's getting kind of rough then. So, makes sense?
So if it says like the specific heat capacity of iron is like 449.4 joules, is that just giving us in joules? Like if it was in kilojoules, it would be 0.4, right? Or 0.0?
Joules per gram.
Yeah, it says no, it says joules per kilogram per Kelvin.
Ah, then it's joules per, yeah. So what is it in simple?
Like it's
is
confusing me because whenever we did a problem, you gave us a specific heat of iron. It was like 0.0. And now it says like 4. Is that just because it's joules instead of kilojoules?
Wait, what? Okay.
It says, okay, this is not for this problem. It's just a specific heat capacity of iron is 449.4 joules per kilogram per Kelvin.
Yeah, so 0.4 kilojoules per kilogram per Kelvin.
Oh, okay, so because like the water would be the other way, so I have to convert it to that in order for my calculations to match up, right? Because if I use this as a specific heat and the water is just 4.4.
Yeah, if you're using kilojoules,
Yeah.
you want to be consistent, yeah.
Okay.
Okay. Any other questions on the homework? All right, it seems to be a little bit of a tricky one, so, or it can be. So, it's due tomorrow, by the way. Also, we do have lab this week on Thursday, right? It's the last lab. Everything will be done in the notebook. And so you'll do kind of a lab report in the notebook. I'll probably post, I was thinking we might do a lab test based on previous labs, where you would just look at your notebook and just based on your notebook, could you reproduce something? But what I'm thinking I'm gonna do is probably we'll just do a new lab. Simple one, kind of one that a whole group can do. And just see whether just on your own you can do all the error analysis associated with that, okay? And do it all in your notebook in that 2-hour period. So we'll probably do the pendulum. So if you review a pendulum, pendulum's an example of simple harmonic motion, at least how we'll treat it. And so the frequency of the pendulum, just so you remember, square root of g over the length of the pendulum. We'll probably do something with that, okay? The angular frequency of the pendulum. And I'll post up that lab soon as I get the chance.
Okay.
But it shouldn't be, I doubt it's something that you can really work much ahead on. And it won't be real. Okay, so today I'll probably do the last little bit of semi-new material, although it's not going to be tested over, it's just more or less for your own edification. And this is second law of thermodynamics stuff. Last time we derived what we called the efficiency of an engine. And the maximum possible efficiency equals the efficiency. And what this is, if you recall, if I had a system or which we can think of as the engine maybe, operating between two temperatures, which is how engines work, heat engines work. If I have a certain amount of heat going in, Q2, and then some heat has to be going out to a second temperature, and in the process of this, the engine outputs some work. And the efficiency is defined as the work that's outputted divided by the amount of heat that it takes in, which is Q2. Now, by conservation of energy, we know that Q2, if that's the amount of energy that's taken in, that would be the amount that's also leaving. So we could write it like that. So work would be Q2 minus Q1, and I can plug this into here. Over Q2. Make sense? So, assuming that the heat capacity of whatever's doing the work inside and we'll just make this assumption. Well, each of these Q's turns out to be proportional to the temperature at which we're putting back the heats here. Okay. We didn't derive that. Deriving it's actually a little bit tricky, but we'll just say that Q2 is equal to some constant times T2. If I increase T2, I'll increase Q2. So if I double the high temperature, in a given amount of time, twice the amount of heat would flow to the engine. If I double the T1, and then Q1, we'll say also is proportional to T1. And this is a little subtle, but it turns out to be same constant of proportionality. And I'll just plug these things into here. This is unfortunately, that's a little bit beyond the scope of class to prove that. So we're just driving a formula based on something that we're not really proving, but at least we know what our assumptions are. So we're doing A T2 minus A T1 divided by A T2. T1. By the way, this A here, as I'm writing A, that's proportional to the change in entropy, we call it. But we're not going to worry about it then. And then I notice how I can factor out an A from here. So A T2 minus T1 divided by A T2. And I get T2 minus T1 over T2. And so the ideal efficiency of an engine is max efficiency. This is because this is for a reversible engine Carnot cycle, is T2 minus T1 over T2. That's what I wanted to derive. And no engine can be more efficient than that, operating between two temperatures. That's the maximum possible efficiency you can have. And so you can start to examine kind of the limits of what you can engineer based on this formula. So actually typical car engines rarely work much above 100 degrees C. That's the boiling temperature of the radiator that cools them. So they don't like to have it too much hotter than that. And so if you have a car engine, T2, and I actually looked this up to be sure about this. T2 was about maximum 100 degrees C usually. And then T1 would be whatever the environmental temperature is, the temperature of the outside. That's how the engine gives off its heat. So, I don't know, you can take like a normal 70-degree day. Let's just test that out. So, 70 degrees in Fahrenheit, what's that in Celsius roughly? 70 degrees Fahrenheit. What's that in
21?
Celsius?
Is it 21? No, I don't know if I did my math right.
Why don't you go see if you can remember how to do that? Good review.
That's right. 21.1.
21?
Yeah, that's what I got, 21.1.
Okay. Good. So what would this be in Kelvin?
At 273. 294. Wait.
Okay. Let's just call it 294, so we don't have to worry about that, okay? 294 Kelvin. All right, what was this in Kelvin?
In Kelvin?
Yeah.
372. Why was it?
0.15, we're not gonna worry about that 0.15, okay? Stay slightly below boiling. Okay, so these are the operating temperatures, the high and the low temperature. We have to do it in Kelvin, by the way. This part, it doesn't matter whether you do it in Kelvin or Celsius because you're taking differences of temperature, but this is an absolute one here. So you need to be in something that starts at absolute zero. So for a normal car engine on a normal day, you get 373's the higher temperature. Actually, I'm going to leave off the units because this will be Kelvin here divided by Kelvin. It doesn't really matter the unit, what the units are at that point. They'll cancel out. Minus 2, what's that?
294.
294 all over 373. So what's the efficiency of that? Got it?
0.21.
Good. Make sense to everyone?
The units of that.
It's a Kelvin over Kelvin. So no units.
units.
That's just the efficiency. This is just the ratio of the heat that's absorbed by the engine, or the work that's outputted by the engine over the heat that's absorbed by the engine.
Is that gonna be, is this stuff gonna be on the test?
No, I don't think so.
Okay.
It's for your own edification. And that's the maximum possible efficiency that you can have for an engine. Anything higher than, yeah, you can't do any better than that. So, if you want to improve an engine, what should you do?
Make the temperatures closer to each other.
Okay, so if I put the two temperatures closer to each other, this gets smaller on the top, right? So we don't have, so that actually lowered the efficiency.
Mm.
So what we want to do is we actually want to have this as big as possible on the top to have the maximum efficiency. So T1, that's kind of hard to go much below the environmental temperature. So T1's probably just going to be temperature of the outside, kind of fixed. So T2 you can deal with a little bit. So if you have a temperature that's running hot, an engine that's running at higher temperature, it will actually be more efficient. And so if you want to make things more efficient, you increase T2. And so that's the goal, is to increase it as much as possible. Yeah.
So is that saying that an engine is more efficient in the winter than like summer temperatures?
Yes. You should get better mileage in winter than in summer. A little strange, isn't it?
Well, it should be like
Yep. In fact, that was actually an example problem I wanted to do. Was let's say that, let's say you can look at the difference. Let's say that you're at summertime, hot day, 40 degrees C. Efficiency equals what for a car engine? And in the wintertime, let's say you're negative 10 C, cold day. Well, negative 10 C is not that bad.
No,
So it's like, 10 degrees.
10 degrees.
Eta equals what? So let's give it a try and see. Well, we can do it here. So T2 would be 100. T1 would be 40. So T2 minus T1 would be 60 for this one, right? And that'd be the same in Kelvin. Over T2, which would be the C373 Kelvin. So this would be, what would that be?
0.16.
So you're running at 16% efficiency, in the summertime, on a hot day in the summer. But it's a cold day in winter, then I'd get 110 difference Kelvin, from the operating temperature of the engine to here. 73 Kelvin. And this is,
Almost 30%.
yeah, 0.29.
29.
So almost 30% efficient. So go ahead and check those out sometime when you're driving around. Just see if you get a little bit better in winter than in the summer. So.
Lose it when you do a preheat car.
Well, yeah. I mean, you have to heat up the engine and stuff
Yeah.
to be that efficient. So.
So it just
Yeah. Make sense? Okay. So there's a couple things that you could do if you're, have to increase your efficiency. The most efficient engines that they make are the ones that are used in giant power plants, as you would expect, right? And these engines are actually kind of interesting. They're turbine engines. anyone know how a turbine engine works? So instead of a piston compressing things in a cylinder, you actually have turbines forcing air in and compressing it that way. And then the air comes rushing in and actually spins the turbines. So I mean, it's even, you know, it kind of works. It works a little bit like that. Air rushing out will spin them. And so basically, it's the same idea as a piston engine. It's just your mechanism of compression is a bit different. And so the most efficient engines are 50% efficient. So let's say that T1 is equal to about 290 Kelvin. Now let's say eta 0.5. What's T2? Question mark. See if you can get that real quick. Got it? What did you get?
580 Kelvin.
Yeah, just twice that, right? Okay. So, the way we got that is, you know, you just plug in 0.5 here, solve for T2.
How do you do it? Can you show?
Okay. So you get 0.5 is equal to T2 minus 290 over T2. Work that over here. So T2 times 0.5 is equal to T2 minus 290 Kelvin. Bring that over here. So you get minus, so 0.5 T2 minus T2 is going to be minus 0.5 T2. Multiply both sides by 2, and you'll get that T2 is 580 Kelvin. And that's on the order of roughly 300 Celsius, which is pretty high. You're talking about 600 Fahrenheit, something like that. So the issue with those engines is you have these turbine blades made up of many, many finely machined pieces of metal, spinning very fast, pressing air in, and having to deal with pressures, and they're all heated up to 580 Kelvin, at least on one end, one side of the turbine. And so the engineering behind that, how to develop those materials that can survive that heat without becoming plastic and moving. That's the real, there's been a lot of work that goes into that. The development of all these super alloys of nickel, for instance, comes from all of that. So they don't use ceramic because it's not tough enough for the high speed. It's not strong enough. So these are high tensile strength metals, and that need to be able to deal with high heats too, without warping, because they're all carefully designed for the aerodynamics in turbines. And so they've not done it with ceramics. The piston engines, they've tried to do that with ceramics to make the piston engines be able to run at higher heats, but I don't think they made it that far yet.
I thought the jet engines at the Rolls-Royce people were making.
Maybe the jet engines, yeah, but they're turbine engines.
They don't get hot.
Yeah. Oh. I haven't heard of that actually, but I can believe it. The jet engines might be different. So, anyway, makes sense.
Can we review for the final?
Oh, review for the final already?
Yes.
All right, one more thing, 2 more things with this and then we're good. So one, there's a big idea, pretty regularly, you run into people that notice that, hey, the Earth is at, 250, 270, 280, 290 Kelvin. And that's a heck of a lot of mass in that Earth, and it's just right there. And so there's lots and lots and lots of energy in the Earth, and just in terms of motion of molecules. And they go, wait a second, why can't I use that to generate electricity? And you run into that quite a lot. Well, I mean, it's a ton of energy right there. You could, generate a heck of a lot for a long, long, long time, just using the heat in the ground. And, you run into that periodically, and the issue is this thing here. If you're trying to take the heat from in the ground and generate electricity with that, you need to have a lower temperature at which you can dump it into. Well, what is that lower temperature? Normally you dump it back into the ground, and so, I mean, it's hard to get that difference in temperatures going with just the ground there. And so you run into trouble with that, and if people are just saying use energy in the thermal energy to generate electricity, and they don't find a place to put the heat that gets brought into the engine, you know that it's probably not going to work. So, a lot of experiments to try and beat this, and unfortunately, it doesn't seem to ever work. So, okay, so you need difference in temperatures. You need some place to dump heat. And then finally, refrigerators. If you took this kind of picture here, this is a lower temperature, higher temperature work done. A refrigerator cycle is basically this run backwards. So it's the Carnot cycle run backwards. So the idea behind a refrigerator is that you take the lower temperature, you take heat from the lower temperature, you do some work on whatever is compressing it, and out goes heat to a higher temperature. Okay, or Q1. So it's basically the backwards of the heat engine is a refrigerator. And the efficiency of a refrigerator, which is called the coefficient of performance, sometimes like this, coefficient of performance of a refrigerator. I might just call it a little epsilon here, Greek letter. That would be the amount of heat that's taken out divided by the work that's put in to do that. So this would be Q1 divided by the work. Now this work would be the same thing as what it was before. It's the work would be, well, Q1 plus work is equal to Q2. So work is Q2 minus Q1. So I can do Q1 over Q2 minus Q1. Now each of these is proportional to temperature. So we could say that this is T1 over T2 minus T1. And that's the coefficient of performance of a refrigerator. So for instance, an ideal refrigerator, if I wanted to take out, what the amount of work that I have to do to take out a certain amount of heat would be just this ratio. So lower temperature, for instance, we can think of a refrigerator like a freezer or something where it's about freezing. Maybe just normal refrigerator about freezing. So 273, and then take it out to room temperature, 293 minus 273. And you could get a pretty good ratio of the amount of work you do to the heat that you pull out. So 20, be about 27. Okay. So with refrigerators, you get pretty good efficiency. I take out 27 times more heat in the work I put in. Make sense? And refrigerators actually,
What do you say?
yeah. Oh, oops, half that. Oh, just half that.
13.
Very good. Make sense? So refrigerators are more efficient than heat engines. And actually, this is like an air conditioner too. One of the most efficient types of heaters is actually taking an air conditioner and running it backwards. So imagine a window air conditioner. You take the colder air from inside and do some work on it and make hot air go outside. Okay? Well, just rotate it around and put it backwards. You take the colder air from outside, do some work on it, and hotter air comes outside, and you've removed a bunch of extra heat from outside and put it on the inside. So those are called heat pumps. Big buildings use these. And they're very efficient ways of heating up interiors of buildings. Okay? That makes sense? All right, there. We can do reviews now. Just wanted to mention those things. So, maybe just write up the topics that we covered. Okay. So topics that we've covered. Started out a little bit of a math review, right?
Is that gonna be on the phone?
We'll be able to do that stuff. But we did a vector addition, triangles. So there's certainly possibility of adding vectors or breaking up vectors into x and y components. Adding vectors, finding components, finding magnitudes, angles of vectors, all that stuff. So that's kind of a prerequisite for much of what else we did. The next thing we did is sort of an example of it. Did we do kinematics first?
Mm-hmm.
So, or do the second law.
I'm pretty sure we do kinematics first.
So we did kinematics, which is the relation between position, velocity, and acceleration. And in particular, you had to work with the kinematic equation, x or y at any time would be the initial y position plus the initial velocity in the y direction times time, plus 1/2 the acceleration in the y direction times squared. This would be the relation between position, a component of position, and acceleration and velocity. Also, Vy at any time should be the initial velocity plus the acceleration times time. These two things, and then same thing with x and y, were really big starting point for dealing with these things. And then we did things like projectile motion based on this. Projectile motion. After that, things like how far something slid down the plane in a given time, or time it takes to slide down something. Various problems like that when you know acceleration. After that, or maybe it was before, I'm having a hard time remembering.
No, now
the order.
we go into newtons first, or whatever,
Yeah.
units of force.
Good. We did force and Newton's second law. Okay. What is Newton's second law? The sum of forces on an object. That's important. Is equal to mass of the object times the acceleration of the object.
Mhm.
And so we did a lot of work with this. If you notice, it's just all you're doing is you're adding vectors. We set these up always using free body diagrams. It's a nice way to start adding vectors. And a lot of times we did statics. I think we did circular motion first, and then statics.
No, we did statics first.
Statics
Yeah,
is
statics.
an example where sum of forces is equal to 0. And also that the moment, or the sum of torques, is equal to 0, where torque is equal magnitude of F times the perpendicular distance from where it might rotate about. This will tell you all sorts
Oh,
of
yeah, we did
things.
circular.
Then we did also circular motion. Another application of Newton's second law. In this case, the acceleration is equal to v squared over r, and it points towards the center of the circle, which is at minus r half, I think. And so I sum up force and set it equal to this if I have circular motion. And m times that.
Wait, is that r over r?
R hat
Oh,
over
R.
R. R hat's a unit vector pointing outwards from a circle, so minus R hat points towards the center of the circle.
Is that negative?
Yeah. That's minus R hat. That's for the direction. What's that?
Is that negative v squared r?
Yep, that's right. And you could also write this as minus omega squared r hat, because omega is angular frequency, and omega was v over r. For the speed of something moving around the circle divided by the radius of it. Six, what do we do after that?
Power and stuff.
Oh yeah, work and power. Let's make this a nice omega to distinguish it from a work. So work was equal to force, distance, cosine of the angle in between the force and distance moved. This is the work done by a force. The total work, the sum of all the works done on an object as it moves along, is the change in kinetic energy. The rate at which this is done is power. If I have what's known as conservative forces, I can treat the work done by them as a negative of a change in potential energy. So conservative forces, this would be like gravity and spring forces. This is, the kinetic energy plus the potential energy is equal to the total energy that we call, and that's a constant. Okay. And if all you have is conservative forces acting on it.
Equals the total energy or just?
Yeah. And that's a constant. You treat that as a constant, and then you can see how things would change. Or, if it's not a constant, you can say that the change in the energy is the work done by non-conservative forces. Although we didn't really talk about that much. The rate of change of energy is called a power. We talked a little bit about that. Or work over time, we could talk about that being a power. I think after that, well, I've probably got a few more things that we need to cover. I'm running out of time now. We'll finish up the list tomorrow, okay? And after that, here's some examples.
We're gonna get a question if you want to.
All right.
Yeah.
Okay.
But I can't tomorrow or.
Yeah, that's fine, that works.
11.
Well, that's wrong.
Oh, yeah. It's like,
And like, you make it up.
Well, to make it, yeah, slowly with respect. Yeah, but slowly with respect.
That far was the only time. We only had 5.
So it's slowly with respect to the time it takes to
Getting your insulation in and out.
What kind of problem were you thinking about doing?
What's that?
Getting something insulated and not insulated.
Well, it's not that bad.